Welcome to LVing, a static analysis framework for detecting memory safety and concurrency vulnerabilities in Rust programs through graph-based pattern matching. LVing's novel approach transforms Rust source code through LLVM intermediate representation into code property graphs stored in Neo4j. This enables vulnerability detection through sophisticated cipher queries that traverse multiple graph relationships simultaneously: abstract syntax trees, data flow graphs, execution order graphs, and program dependence graphs. The system runs as three containerized services: Nginx frontend, a fast API analysis engine that automatically annotates variables with tracking metadata, and a Neo4j database. This architecture enables interactive, real-time vulnerability analysis with synchronized multi-level code visualization. Let me demonstrate LVing's capabilities using a concrete example. I'm selecting the data race example from our built-in vulnerability dataset. This code demonstrates a classic data race condition in Rust, one that bypasses the language's safety guarantees through unsafe operations. Here's what's happening. The code creates a raw pointer to shared data and wraps it in a custom sendable PTR struct. By implementing the send trait unsafely, the code allows this raw pointer to be transferred across thread boundaries. Two threads are spawned, and each directly modifies the value through the raw pointer without any synchronization mechanism. This is problematic because multiple threads are concurrently writing to the same memory location. While Rust's type system normally prevents such issues, the unsafe block circumvents these protections. The result is undefined behavior, a genuine data race that could lead to memory corruption, inconsistent program state, or crashes. This is exactly the type of vulnerability LVing is designed to detect and visualize. Now I'll click Convert and Export to Neo4j to initiate LVing's analysis pipeline. Watch as the system processes this code through multiple transformation stages. First, LVing injects necessary headers and automatically annotates variables with metadata to track their lifecycle. The enhanced code is then compiled to LLVMIR with debug information enabled. The output shows the pipeline in action, waiting for Neo4j to become ready, creating the database schema, and executing the CPG translation. Notice how LVing reports the node counts: over 50,000 AST nodes and thousands of other graph elements representing the complete program structure. The middle panel now displays the full LLVM intermediate representation. This low-level code shows exactly how the compiler translates our Rust program, including all the intrinsics for thread spawning, pointer operations, and synchronization primitives. Every instruction here is now represented as a node in our graph database with rich metadata and relationships. Now for the powerful part: graph-based vulnerability analysis. On the right panel, I'm opening the query dropdown and selecting our execution order graph query. This query specifically searches for our annotated variable and traces its execution flow through up to 6 steps, looking for binary or unary operations, the exact operations that perform the unsafe modifications. The query executes, and we immediately see the vulnerability pattern visualized. The graph shows 21 nodes representing the execution path of our vulnerable pointer. Each node represents a program statement, and the edges show the execution order, the precise sequence of operations that leads to the data race. Here's where LVing's innovation really shines. As I hover over any node in the graph, the corresponding LLVMIR code is automatically highlighted in the middle panel. More importantly, the original Rust source code is simultaneously highlighted on the left, creating a three-way synchronized view. This means security researchers can see the vulnerability at 3 levels simultaneously: the high-level Rust code developers wrote, the low-level LLVM instructions the compiler generated, and the abstract graph representation showing the program's control or data flow. This synchronized visualization enables analysts to visually trace execution paths and identify vulnerability conditions across 3 abstraction levels simultaneously, eliminating the need to manually correlate source code with compiler output. LVing supports 10 distinct vulnerability categories through custom cipher patterns, enabling researchers to develop new detection techniques. By combining compiler-level precision with graph-based pattern matching, LVing provides a powerful platform for security researchers, developers, and educators to discover, understand, and eliminate vulnerabilities in Rust programs. Thank you for watching this demonstration.